Hello everybody. I wanted in this post-lecture video to conclude what we were saying yesterday regarding the p-n junction. There was only one thing left to discuss, that was the diffusion capacitance. and so that's basically what I wanted to show you here. In this part, actually, we will also, just because it's related to that, see also the differential resistance related to the p-n junction. And also I discovered that I made a small mistake yesterday when I was really at the very beginning when I was talking about at a certain point some potential and so on. The final result was correct, but I did a mistake that kind of cancelled out two mistakes that cancelled out regarding a sign, basically. So I will briefly correct that. And as I discuss this thing about diffusion capacitance, I will also point out, as I said, because we will be discussing the differential resistance concept, I will also point out which is the difference between DC resistance and differential resistance. This is something we will come back many times. So as I said today, repetition is good. So I will address this here today as well. So have a look at the video, and I'll see you next time. So yesterday at the lecture, we realized that the p-n junction operation electrically relates basically on drift and diffusion, and when we apply some voltage across the p-n junction, what we do effectively, we bring the system out of equilibrium. And as we were discussing yesterday, if you remember, I had shown you some nice graphs, these ones here, that give you a representation of the actual charge distribution, both for holes and for electrons across the junction when it's forward biased. And if you remember, we discussed here the fact that on the p side, for example, which is this side here, these are the density of electrons, which are the minority carriers, and these in forward bias condition, this density can be quite different from the thermodynamic equilibrium value. Actually, this can be huge, because as we said, in this low injection assumption we are making, the only restriction effectively we are doing is that the minority carrier density should not overcome the value of the majority carrier density at play. So really, in this case, the majority carrier densities are these and these. So really, the upper limit for these minority carrier densities up to here, effectively. So we understand that this minority carrier density could be hugely different from the thermodynamic equilibrium value. And this is actually the key to understand the diffusion capacitance. So if I go back to the part we are dealing with today here, so the diffusion capacitance arises exactly from the fact that when the junction is out of equilibrium, particularly forward biased, there is a huge amount of charge, both electrons and holes, that are actually accumulated in the proximity of the junction, simply because the junction is now conducing current. And in this regime, we said mainly is by diffusion. That's why it's called diffusion capacitance. So we have positive charges here, negative charges here. These are huge, remember, are a huge amount of charges. Because as we said, this non-equilibrium situation can induce the minority carrier density to be actually, in this non-equilibrium situation, to be actually huge as compared to the thermodynamic equilibrium. So a huge amount of positive charges, a huge amount of negative charges. This means separated by the depletion region, which in forward bias, which will also be small. This means that the diffusion capacitance is huge. Remember that the capacitance in general is inversely proportional to distance. So in forward bias, this distance is small. So clearly this shows that the diffusion capacitance has to be really big here, also because we have a lot of charge that is being accumulated. And indeed, that's what the diffusion capacitance does, is extremely big in forward bias, but in reverse bias is actually negligible. And so we, as we discussed also the depletion capacitance, we should keep in our mind the following picture, that the diffusion capacitance, which is this red line, is actually zero effectively in reverse bias, and then picks up exponentially, as we will see in a moment, and grows exponentially. And so effectively in forward bias is actually what the capacitance that dominates over everything else, while the depletion capacitance actually matters in reverse bias, as you can see, is effectively non-zero, is the only one that is non-zero. So in reverse bias, what matters is the depletion capacitance, very roughly, and in forward bias, really the depletion capacitance. As you can see, the total capacitance would be the sum of these two. Remember, these two capacitances are effectively in parallel. So let us have a look at how we could find out the diffusion capacitance. The way we calculate, we demonstrate how much it is by using the small signal method in its most fundamental approach. That is the one that, as we've seen in chapter 1, when we explained what the small signal method is, we used, if you remember, the step-by-step approach, which is, let us assume that this is my device and we apply a signal that is effectively the sum of a DC voltage plus a small AC signal. So we imagine now to apply this technique to the IV characteristic of our device, which is the PN junction. So we just found it, and so we have to effectively substitute this quantity into the IV characteristic and then separate, as we will see in a moment. Now, by doing this effectively, we will demonstrate also, or maybe go through, we will find also the differential resistance. Because also, you remember, the differential resistance relates effectively, is found maybe using a similar approach. So, but the only thing is that we need to use, in this case, to find the diffusion capacitance, we need to use this, let's say, we have to start from zero, let's say, this method, just because, as we will see in a moment, we need to add a more detailed step to be able to see the diffusion capacitance, because otherwise, if we were interested just in the diffusion, in the differential resistance, we've already highlighted in chapter 1 how we find it for a nonlinear component. So I'm kind of doing something here that we've already done, but there is a reason for this. Okay, so just stay with me. So let's apply the small signal method. So we assume that we are applying at the terminals of our PN junction a signal that is the sum between a DC component, constant V, and a small oscillating signal on top of that. And so we substitute this type of signal into the characteristic of the PN junction. And so this goes effectively into the exponential part. And so we can break up the exponential, and so we can write this thing here. So J is J0 time e to the EV over KT. This is the V that is DC, so it's a constant, time e to the EV tilde over KT, where V tilde now is this small oscillating signal, minus 1. Now, because V tilde is small, we can expand using a Taylor expansion to the first term, this exponential, and so we substitute it with this term here. If we substitute in and separate the terms, we get J0 e to the EV over KT minus 1, which is effectively, this is, V is constant, J0 is constant, so this is effectively what would be the DC current coming out of the PN junction when we apply a voltage V. So this is a DC current, DC J. We call it J. Plus, and this is the term that now is AC, that this is the component of the current that is actually oscillating. And so this is J0 e to the EV over KT time EV tilde over KT. As you can see, the oscillation is the result of the presence of V tilde here. All the other terms are constants. Okay. So this is our AC current, which is J tilde, we will call it. So just to rewrite things more clearly, J tilde is J0 e to the EV over KT time EV tilde over KT. Remember that J0 is this thing here according to our derivation yesterday, which we can rewrite in this way. I'm simply using the definition of that we saw yesterday of Ln and Lp and doing the needed simplifications, and we can rewrite in this way. And this is effectively the point where I wanted to reach to actually start now doing the steps required to be able to use now all these things toward finding the diffusion capacitance. So as you can see here, normally we would put tau p or tau n, which is the lifetime of the minority carriers. These in the n-type semiconductor, these in the p-type semiconductor. But I've added AC. And the reason is that the reason is that tau p and tau n actually depend on frequency, and we will show it in a moment. Oh, remember, just a quick note here, that the DC voltage V and J that we've just identify a point on the IV plane or JV plane that we call, remember, the quiescent point. Okay, we should try to remember this kind of things. And remember, all these, as I've already said, falls into the framework of the small signal model that we've just seen in chapter 1. So here we have our nonlinear IV curve. And so we've identified this is the quiescent point identified by the DC voltage V and the DC current I, which sometimes we indicate also as VQ or I and IQ. And then what we are thinking of doing is that on top of this signal V, we apply a small oscillating voltage V tilde, we called. And so by result, Q will oscillate a little bit around this point. And so this means that on top of the DC current I will have also an oscillating current I tilde, as we said. This is effectively the small signal method. And in chapter 1, if you remember, we also demonstrated that we can calculate the differential resistance in point Q simply by doing the slope of the tangent in this point represents 1 over the differential resistance. We generally indicate there is a typo here, R small, 1 over Rd, where Rd is the differential resistance. And remember, the slope is di over dv, calculated in this point. Okay. Just to conclude now this thing we just said about reminding ourselves about the small signal model, remember that the relation existing between DC resistance and differential resistance. So let's go back to the IV, an IV plot of a nonlinear component. So this is the black curve represents the nonlinear IV curve of a component. So if we pick a point Q on this curve, we can define two resistances. The DC resistance corresponding to this point on the curve, which is effectively represented by the slope of the red line, which is the line that goes through 0, 0 on this plane. And this is what we would call the slope is 1 over RQ, where RQ is our DC resistance, let's say, and this calculated by V of this point Q, which is this value here, and I of this point Q, which is this value here. So if you do V of Q and I of Q, you find RQ. Okay. On the other hand, as we just said, the differential resistance is actually related to the slope of the tangent in Q. And so, and this relates to 1 over Rd. Rd is the differential resistance. So 1 over Rd is the I in the V calculated in Q, and so Rd is the inverse of that derivative. Okay, so in other words, RQ relates to the quantities, the DC quantities that are that are identified by Q, while Rd relates to the derivative to the nonlinear curve in Q. Okay, so DC resistance, differential resistance. The differential resistance, remember, is important when we are using small AC signals, while obviously the DC resistance is important when we are dealing with DC signals. So just to put it clearly in writing, which is the differential resistance for the PN junction. So using what we just said, the differential resistance Rd for the PN junction is found by doing di dv, the inverse of di dv calculated in a specific point Q of the curve. And so we do d dv of the IV characteristic of the PN junction, which is I0 times e to the EV over KT minus 1. So we do this derivative against V, and this derivative is this quantity here. I need still to invert it, so I invert it here, and I've also calculated in, you see, I need to calculate in a point Q, and the only way to identify Q in this formula is by using V of that specific point Q. So I put here VQ, as you can see. So what do we see? We see that the differential resistance, for example, is V. If V is in forward bias, so V is positive, this exponential is going to be very big, and so the denominator is very big, so we understand that the differential resistance is extremely small. Okay. While if V is negative, the exponential is going to be very small, and so the differential resistance is going to be very big. Okay, so this was just since we started this part by mentioning the small signal method, this was just to apply now the small signal method to the PN junction using what we already know. So how to calculate the differential resistance for the PN junction. So let's go back to where we were before we digressed a little bit on this point. So we were here. We had found J tilde for our PN junction, the AC component, the AC current, as a function of V tilde, the oscillating AC small voltage signal. And remember that we had expressed J0 in terms of the different parameters here, and we said that, remember, tau is actually a function of frequency, and we can demonstrate that now. We will mention this now to continue then our investigation. So using some of the results that arise when we do the demonstration for the JV characteristic of the PN junction, we can actually demonstrate that the lifetime tau p or tau n is actually a function of frequency, as written here, this type of function of frequency. So tau p is actually the general frequency function is tau p, the one that we also have seen some time ago in semiconductors in general, divided by 1 over 1 plus j omega tau p. So as you can see here, I've also wrote it explicitly. When omega goes to 0, tau p AC tends to tau p, to the value that we defined some time ago. Okay, the same for tau n AC. So we substitute these things into J0, and so finally we can write the final expression that we will use now to find the diffusion capacitance and refine also the differential resistance for the PN junction. So from this equation now, what do we do is the following thing. You see now that these two terms contain omega, and it's in a quite complex form because it's the square root. So normally when we deal with complex numbers, the square root is quite difficult to handle. So what we need to do though is to do a Taylor expansion. That's how we deal with that. And so when we do the Taylor expansion of this quantity looks like that, the first few terms. So the Taylor expansion of this would become this one here. What we need to note is that there is one term that has no omega dependence, and then all the other terms do have an omega dependence. And in our mind, we start separating these two. So as I did here, we could think of writing this as one, the term that has no omega dependence, and all the rest, but written in a clever way, j omega time all the rest. As you can see, all the rest is also made of a constant and something that depends on omega. We will come back to this in a moment. Now, remember that when we have a resistor in AC signals, I tilde is equal to 1 over R V tilde. Or if you like, I tilde is GV. G is the conductance, if you remember, which is the inverse of the resistance. If we have instead to deal with a capacitor, I tilde would be J omega C V tilde. Remember, this is would be 1 over Z of the capacitor. So, and that's what it would be. So you start probably realizing why I've done this conceptual thing previously. So if I had a resistor, the relation between current and voltage would have been through a constant. If I had to deal with a capacitor, the relation between current and voltage would be through a term of the type J omega something. J omega something. So we realize that what we've done up here by effectively expanding by Taylor these terms is actually show that the relation between J tilde and V tilde relates to both a resistive component and a capacitive component. And that's what I try to highlight further here. So J tilde relates to all the other terms, you remember, where was also V tilde, through a first term that has no omega, and J omega, some other terms which even depends, some of them on omega, and this effectively is reminding us exactly what we just said. This really looks like J tilde equal a conductance G plus a term coming from a capacitor. Okay, so this type of relation between J tilde and V tilde means through a term that is a conductance plus this is the inverse of the impedance of a capacitor. It's the admittance of the capacitor. So this points us to the fact that there are two elements, a resistor and a capacitor, that are connected in parallel. This is because if GD is the conductance of the resistor and YC is the admittance of the capacitor, which is J omega CD, then this circuit has a total admittance that is the sum of the two, exactly as they appear here. If you prefer the resistance and the impedance, this circuit would look like that. Still in parallel, of course, but this would be now the differential resistance RD, and this would be the what we call the diffusion capacitance. Okay. And so now, having this in mind, we will try to compare now this very simple model to this, having in mind that we have to substitute, the Taylor expansion of these terms and so on and so forth. Obviously, I'm not doing it here. It's quite long, time-consuming. There is no reason to do that. The important is that you understand the conceptual process. And so, for example, looking at the easiest term is the one that is constant, doesn't depend on omega, the one that relates to GD. So we can easily realize that GD, I've added this term F just because I'm calculating it especially in the forward bias condition. So GD is the exact expression is this one, but if we assume that we are in forward bias, you see J0 time this exponential, which is a constant, remember, because V is the DC voltage, this is constant, is actually J in the forward bias condition, is the constant current that we had. If I go back to the plot, is the constant current. Where was the plot? Sorry, I didn't probably put the plot. Is this constant current here, effectively. So we were here. And so in forward bias, we can write GD in forward bias in this way, very simply. Obviously, you can see that this quantity is exactly what we had found previously. So if you do the inverse of GD, this is exactly, if you keep in mind for a moment this term, this is exactly the same as the one that we had found previously here. There you go. Without J, I wasn't using J0, I used the I0 here, but it's the same. So this is GD, and so RD is 1 over all this thing. Okay, so everything, it obviously has to be like that. Okay, so but the nice thing of doing all this mess is that, okay, we demonstrated that indeed we found the result that we already knew about the differential resistance, but now the cool thing is that we can find also the differential capacitance, or better, the diffusion capacitance. And furthermore, based on what we said previously about the fact that from the Taylor expansion, we realize actually that this diffusion capacitance is actually a function of omega. And most important, the first term is constant, which we will indicate as CD0. The second term actually has a negative sign, and is a term, a constant, time omega. Okay, and then some other stuff. It's important just to keep in mind this first term, okay, because it's telling us that this diffusion capacitance we are actually able to calculate with this technique is actually a function of the frequency, and a special function that initially is constant at low frequency, but then as the frequency increases, it will start to drop because of this first term of the expansion. Okay, so the diffusion capacitance is constant, but then it starts to drop in frequency. So, what is the first term? Well, the first term we can demonstrate is this thing. Okay, all these are all constants, and then the term that depends on the specific quiescent point we are working at on the nonlinear curve of the component, and time E over KT, and so which we can actually rewrite in a bit more concise way in this way, using LP and LN, the diffusion lengths. So finally, we can say that the first term in our expansion of the diffusion capacitance is CD0, which in forward bias, well, this is the general expression here that we said previously. If we specialize to the forward bias, using the fact that, remember, in forward bias, J is effectively J0 time e to the E over EV over KT. We are basically saying that the exponential is much bigger than the -1. That's all. And so if I wanted to replace here some terms to make appear, JF, the value at the quiescent point of the current, so I should multiply and divide by J0, so that J0 time E to the EV over KT is JF, which I made appear here, and so everything has to then be divided by J0. And so this is the most compact form in forward bias we can think of for the first term of the diffusion capacitance. So as you can see, it depends on JF, obviously. It is exponentially dependent on the voltage of the quiescent point I've chosen, or if you like, it depends on JF, the current at the quiescent point on the curve. So it can be extremely large in forward bias. That's the point. And now, regarding reverse bias, we've already anticipated that the differential resistance is extremely large, and at the same time, we can say that the diffusion capacitance, simply by judging false again and using similar arguments as the differential resistance, because of this exponential term here, if V is negative, so our quiescent point is in reverse bias, so V is negative, this exponential term is extremely small, so the diffusion capacitance is effectively 0. So, and that's why we said since the beginning that the diffusion capacitance is actually big only in forward bias. And so finally, for our PN junction, we can now define, once we have defined, differential resistance, we've talked about depletion capacitance, we have defined the diffusion capacitance. We can now develop a small signal equivalent circuit of our PN junction. So this is extremely useful if we want to apply to a PN junction a small AC signal. Okay, so in our mind, if we have this circuit in front of us, in our mind, we should replace it with all the components we just talked about. So the PN junction becomes effectively this: a differential resistance, depletion capacitance, diffusion capacitance, all in parallel. Now, we can simplify this equivalent circuit depending on where we are. So in forward bias, as we said, what dominates really is the diffusion capacitance, and so we can simplify the circuit simply with the differential resistance in forward bias, which is extremely small, and the diffusion capacitance, which is very big, and so the impedance is very small. So, that's why they both play an important role. This is small, the impedance of this is also small, because in general, this is big. Obviously, whether it is in the end big or small, it will depend on the frequency, because remember the impedance of the capacitor is 1 over j omega c. But let's say in principle, this also could be small, because the diffusion capacitance is generally extremely big. In reverse bias instead, we have to drop out of the model the diffusion capacitance, which we said is very small. And so in principle, we should have the parallel between the differential resistance in reverse, which generally is very big, as we said, because of the exponential dependence on the voltage, and the depletion capacitance, which is quite a smooth. This doesn't change a lot. Remember that the depletion capacitance, as we discussed last time, is given by the dielectric constant of the semiconductor divided by the depletion layer width. And the depletion layer width has a very, doesn't depend exponentially on the voltage, as a square root of some voltage. So compared to the exponential dependencies on voltage that we've seen for the other, for the differential resistance and the diffusion capacitance, so this can be regarded as a very smooth function. So going back to the model, so that's why the depletion capacitance is important in the reverse regime. Because the differential resistance is extremely big, we could actually in most cases neglect that. So in most cases, actually in reverse bias, the equivalent model of the small signal model of the PN junction is actually just the depletion capacitance. As simple as that. Remember that both the depletion capacitance and the diffusion capacitance depend on voltage, on the DC voltage of the quiescent point. So regarding the diffusion capacitance, remember that this is the voltage of the quiescent point on the curve. So if you change the quiescent point we are working at, this will enormously change the diffusion capacitance. And also, the depletion capacitance, as we just said, depends on the voltage. The DC voltage. So the voltage of the quiescent point. So we realize at this point, obviously the diffusion capacitance is the one that depends very, very strongly from this voltage. So anyway, what is important is to realize that the PN junction, the capacitances involved in the PN junctions are really cool, because they have this enormous, especially the diffusion capacitance, this enormous dependence on the voltage. So they are effectively variable capacitances. And this is something that is really important in some applications. There are lots of applications where this may be needed. Have a tunable capacitance, okay? And you can tune it simply by changing, as we said, the voltage V, the DC voltage at which you are operating the PN junction. You are biasing the PN junction, which, remember, on the curve is this point here. Okay, so by moving this point, this voltage V up and down, you are enormously changing the diffusion capacitance of the circuit, and this has enormous importance. So the depletion capacitance depends on voltage in a very smooth way, though. The diffusion capacitance depends enormously on voltage, and is very important, is huge actually, the diffusion capacitance in forward bias. But on top of that, the diffusion capacitance is also a function of the frequency of the AC signal. Okay, so try to think about these things I've mentioned to you, and let me just, this completes the diffusion capacitance. I wanted just to mention to you the little thing that I did a mistake about at the beginning of the introduction, let's say, on the PN junction. So if you remember, in the beginning we were talking about generally energy diagrams and why they change what happens when you apply voltages and so on. So at a certain point I was trying to calculate this quantity here, Vx minus Vb. So while I was doing the calculation, I said, okay, dl is actually going in the opposite direction of the x-axis, so this is minus dx. And here is where I did a mistake. Here I wrote that this was minus E, the component of the minus E x. So this was not correct. So really, this is the correct answer. I've also obviously modified my notes to take this into account. So the correct thinking is, this is by using the definition of voltage, so minus the integral over a path that goes from B to X, as I've indicated here, from B to X. This is the path, L from B to X of this quantity. But just because this path goes against the x-axis, I wanted to use a path that actually goes in the right direction of the x-axis. So I want to use this path, L, that goes from X to B. So if I invert the direction of the path, I need to put to change sign to the entire integral, remember. So I minus the integral of the path that goes from X to B. So in this situation now, indeed, the dl is actually dx, E is actually the component along the x-axis, and so these two minus obviously cancel out, and this becomes the integral from x. We are going from x to b, so the integral goes from x to xb on the x-axis. And so we find the result. The final result is correct. Yesterday also I did put the right results, simply the explanation in between was erroneous. I did twice an error in sign that cancelled out. Okay, and really that's it for this post-lecture video. So have fun, and I'll see you next time. Bye.